In this vodcast, we'll be looking at ray diagrams and equations for concave mirrors. The rules for drawing the ray diagrams for concave mirrors are very similar to the rules for lenses. The difference is that rays that hit a mirror reflect, where rays that hit a lens refract or bend. There are three rays that you can draw to find the location of an image. So in this diagram, what I've got is my concave mirror. And the concave mirror is defined by its center of curvature. The distance between the center of curvature and the edge of the mirror is actually the radius of a circle. So if I go all the way around with this mirror, oops, went too big, it would be spherical in shape, but I've just got a portion of that sphere as my mirror. The focus of the mirror is halfway between the mirror and the center of curvature. The focus of the mirror behaves just like the focus of a lens. In other words, if I draw a parallel light ray, that is parallel to the principal axis, when that light ray hits the mirror, it will bounce off so that it goes through the focus. I would like to point out that this light ray obeys the law of reflection. The law of reflection says that the angle of incidence equals the angle of reflection. In other words, if I draw in the normal, this angle, angle of incidence, equals this angle, the angle of reflection. For the purpose of drawing ray diagrams, you do not need to put in the normal or the angle of incidence or reflection. You only need the parallel light ray and the reflected ray that goes through the focus. However, I wanted to point out that the system is internally consistent. The next light ray that we're going to draw goes from the top of the object through the center of curvature. This light ray hits the spherical mirror in such a way that it bounces straight back. And if I draw a line tangent to the mirror itself, you'll see that that tangent is actually perpendicular to the light ray, and that's why the light ray bounces straight back. The third light ray is optional. You can draw it from the top of the object through the focus, and then when it bounces off the mirror, it goes parallel to the principal axis. Please notice again that it obeys the law of reflection. You can check the law of reflection the way I did here with the angle of incidence and angle of reflection, or you can check these angles as measured from the mirror. Those should also be congruent. Let's look at some thinking questions. Why are the parallel and focal rays drawn parallel to the principal axis and through the focal point? So what the focus does, or where the focus is the focus is the location that all parallel rays will be directed to. Why is the chief ray drawn through and reflected back through the radius of curvature? Again, the reason for this is if we draw a line tangent to the spherical mirror, we see that the light ray would bounce straight back. So the light ray is perpendicular to the surface of the mirror at that point. The rays come together to form either a real or a virtual image. Is this image real or virtual? This image is real because light is converging at the location of the image. So in this diagram, we can see what happens when we draw our three representative light rays, and our image will end up at the intersection of those three. Now let's take a look at the equation for mirrors. It's very similar or identical to the equation for lenses. 1 over p plus 1 over 2 equals 1 over f. Or, since the focus is related to the radius or center of curvature, you can rewrite the equation as 1 over p plus 1 over q equals 2 over r. Again, q is the image distance, p is the object distance, f is the focus, and r is the radius of curvature for the mirror. What is the relationship between radius of curvature and focal length? Again, 2 times the focal length equals the radius of curvature. By the way, sometimes you'll see radius of curvature indicated with an R, and sometimes you'll see it indicated with a C. The magnification equation is the same for mirrors as it was for lenses. Magnification is a ratio of the height of the image over the height of the object. It's also a ratio of Q over P. Let's try an example. It says an object of height 2 centimeters is placed a distance of 9 centimeters from a concave mirror with a focal length of 4 centimeters. Find the image distance and magnification. The first thing I'm going to do is place the focal length 4 centimeters from the mirror, so I've counted from 9 back to 5. Then I'm going to place the object 9 centimeters from the mirror, and then I'm going to mark the height of the object, which was 2 centimeters. Now I'm going to follow my rules for drawing ray diagrams. I'm going to start with a parallel light ray, just like what we did with lenses. I draw a light ray parallel to the principal axis. When it gets to the mirror, it bounces off the mirror and goes through the focus. The second light ray that I'm going to draw needs to go through the center of curvature, so I better draw the center of curvature. If the focus is 4 centimeters away, the center of curvature will be 8 centimeters away. So there's my center of curvature, or my radius of the mirror. Now, I haven't done a great job of giving you a picture that is large enough. The mirror, if it doesn't look big enough, you can just go ahead and extend it. And it turns out that it doesn't matter a whole lot, because really what I'm looking for is this intersection. This intersection right here tells me where the image will end up. So this light ray coming from the top of the object hits the mirror and bounces straight back. Now, in order to find the location of the image, I've drawn everything that I need to draw. If you'd like to, you can draw a third light ray, but it's not necessary. I'll use a different color. This would be for verification. The third light ray would go through the focus and then bounce back parallel to the principal axis. I want you to notice that we end up in the same location once again. Okay, so I've got my object. I just located my image. And with a ray diagram, I can actually measure my image distance Q. Q comes out at about 7.2 centimeters. And my image height comes out at about 1.6 centimeters. Okay, so I could compute the magnification by taking negative height of the image over the height of the object, which would be negative 1.6 over 2, which would be negative 0.8. And this indicates that I have an inverted, or upside down, real image. Now, once again, I can solve this problem two ways. I just solved it with a ray diagram, but I also could have solved it with the mirror equation. To find Q, I could have used 1 over P plus 1 over Q equals 1 over F. Let's see, P was 9 centimeters, and Q was 4. and then I would use my calculator to get Q. I get 7.2. Hey, they match. I'd like you to notice the signs here. In this case, a positive Q value indicates that the image is on the left side. I also have a positive P value. It indicates that my object is on the left side. And my focus at 4 centimeters is also a positive value. Now let's take a look at what happens when we put the object inside the focal length of the mirror. We're going to follow the same rules for drawing rays. I'm going to start with a parallel light ray. That parallel light ray is going to bounce off the mirror and go through the focus. And now I need to draw a second light ray. The second light ray, again, is going to go bounce back and forth from the direction of the center of curvature. So let's think about what's happening here. The first light ray that I drew, the parallel one, bounces off and goes through the focus. The second light ray, the one that is coming from the direction of the center of curvature, is going to bounce straight back toward the center of curvature. Now once again we have diverging light rays. And this should tell you something. Diverging light rays means that we're going to get a virtual image. Again, a virtual image is an illusion. When we create a virtual image, the observer, here's your eyeball, the observer's eyeball, the observer sees these diverging light rays and the brain says these diverging light rays must be coming from a single point. So we extend these rays back. Sometimes I find it helpful to draw them as dotted lines or in a different color to remind myself that there is no light actually converging there. And then our image will be at the intersection of those extended light rays. So here's our virtual image. It's upright, it's magnified, and it's virtual. Now to compute, there's a couple things I can figure out from my ray diagram here. One thing I can figure out is Q. Q is about 2.9. And because the image is on the other side as compared to my first diagram, remember Q was positive here. Now Q is negative. So when we have a virtual image, Q is negative. The magnification I can compute by looking at the height of the image. So the magnification is going to be 2.5 over 2. Eek. 2.5 divided by 2 is a magnification of 1.25, and that's a positive value because it's an upright image. So an upright image is going to have a positive magnification, while an inverted image would have a negative magnification. Can I use the mirror equation in this problem? Yes, I can. So again, I could have solved for Q using 1 over P plus 1 over Q equals 1 over F. I would write, well, first I would have to measure P and Q because they weren't given, so let's check that. So F is at 3.5 centimeters, and P is at 2 centimeters. So I have 1 over 2 plus 1 over Q equals 1 over 3.5, and then I would use my calculator to compute that. 3.5 reciprocal minus the reciprocal of 2. So Q is negative 4.67. Gosh, I'm way off there. 2.9 versus negative 4.67. Okay, let's take a look at another example. An object is very far away from a convex mirror. Where is the image created? Just like with lenses, if an object is very, very far away, then all of the light coming in is parallel to the principal axis. And if all of the light is parallel to the principal axis, then what's going to happen is it's going to be reflected so that it goes through the focus. So the image will be located at the focus. If we look at this in terms of the equation, 1 over p plus 1 over q equals 1 over f, if we put in infinity for p, then essentially what we have is that q equals f. The image distance is the same as the focal length. One more example with concave mirrors. An object of height 3 centimeters is placed a distance of 12 centimeters from a concave mirror with a focal length of 4 centimeters. Find the image distance and magnification. Okay, so object height, is 3 centimeters. Object distance is 12 centimeters. Focal length is 4 centimeters. And we're supposed to find the image distance and magnification. So the first thing we need is Q, and then we're going to solve for M. So I'm going to use the mirror equation again. So 1 over 12 plus 1 over Q equals 1 over 4. So I'm going to take the reciprocal of 4, subtract the reciprocal of 12, and take the reciprocal of that, and I get 6. So Q is 6. And then my magnification is negative Q over P. So that's negative 6 over 12, or negative 1/2, negative 0.5. So this will be an upside down or inverted but real image.